Hi everyone. Hi everyone. Here's one of my favorite topics for teaching to students that are needing extension. Proof is one of those things that don't get done enough in lower school anymore. So let's start with some basic ideas and maybe we'll build them up over the year. So if we're looking at proof, we're trying to show that something is true based on something we know. So in these examples, we're going to use the following. All even numbers can be represented by a doubled integer. If we double something, it's going to be even. Double 3, it's 6. Double 4, it's 8. Double 5, it's 10. Doesn't matter what integer you choose, if you double it, the number is going to be even. The second one is we're going to say that one more than any even number is an odd number. So if we were representing even numbers with 2k, as in double of some integer, so all this means k is a member of the integer set, then 2 times k is always even. Doesn't matter what value you choose in the integer set, it's always going to be even if you double it. Similarly, if you choose any number in the integer set, if you double it and add 1, it'll be an odd number. Double it, you'll get an even number. One more than it's going to be odd. Now, all multiples of k, so if k was a number that was in the integer set, any other integer times that original number will be a multiple of k. So that would look like if we took the number 2 and we multiplied it by 1, we would get 2. We multiplied it by 2, we'd get 4. We multiplied it by 3, we'd get 6, so on and so forth. Rather easy. And similarly, if we have these numbers, if we divide it by this, we should get an integer. And if we do, then it's a divisor of this number. So if we had 42, if we can divide it by 2, and it gives us an integer, we know that this number will divide into that evenly. In this case, the integer would have been 21. 21 times 2 is the 21st multiple of 2 is the number 42. Okay, so like we're on our way now. So we have some definitions. We can do multiples, divisors, even numbers, and odd numbers. A fairly basic set of numbers that you learn in primary school. And then we're asked to prove the following. If A is odd and B is odd, we add them together, show that it's odd. So here's how we would do that with a proof. We'd start with a statement. If A is odd and B is even, prove A plus B is odd. That's what we're trying to do. So if A is odd, that's going to imply that A is equal to 2k plus 1. We know that from our facts above, given that k is an integer number. And if B is even, we can say B equals 2j if j is an integer, because if I double an integer, any integer, I'm going to get an even number. Now what I'm going to try and do is satisfy the condition that it's going to be odd. So I'm wanting to end up with something like 2m plus 1. So here's how I do it. I add them together, take this, 2k plus 1, I add 2j, and then I factorize the k and the j together, so I get 2k plus j plus 1. Now here, I'm going to let m equal k plus j. What's happening here is we know that k is an integer from here. We know that j is an integer from here. If we add two integers together, we always get an integer. So m must also be an integer. So if I substitute m for k plus j, rather than having two integers adding together, I can just say that m is the integer that's formed by adding them together. And thus I get a statement 2m plus 1. Now if I have an integer and I double it and add 1 to it, I know that it's going to be odd. So I can say, therefore, a plus b is 2m plus 1, which implies that a plus b is odd by the property that we have here at the top, as required by the question. And we finish the first one. And what you'll notice is that this sort of proof tends to lend itself to a pattern. So here's the second one. Let p and q be a member of the integer set such that p is divisible by 5 and q is divisible by 3. Prove that pq is divisible by 15. Well, we start with a statement. If p is divisible by 5 and q is divisible by 3, prove pq is divisible by 15. So if p is divisible by 15, that implies that p is equal to 5k, because 5 times some integer will be divisible by 5, by definition. And the same with q. If q is divisible by 3, q must equal 3 times some integer, because that's the set of numbers that are divisible by 3. As we proved up the top, 3, 6, 9, 12, 15, 18. This is the whole set of divisible by 3 numbers. Now, if we want to look at PQ, we can multiply what P is and what Q is, 5K times 3, and we get 15KJ. And similar to before, if we let M equal KJ, we get PQ equals 15M. Now, if we have this here, 15 times any integer is going to be divisible by 15. So we can therefore say it implies that PQ is divisible by 15 as required. And this is a good start to your proof journey. And you can start now thinking about the other types of proofs that we're going to look at that this is the basis of. Thank you, everybody, and I hope that was a bit interesting.